invitation. With Alberto we met long ago in Trieste when I went to Sissa, and he was at ICTP with Jim Hills.
Exactly.
And I knew Jim Hills, you know, for a while. So when I came to Trieste, Jim used to talk to me, and he had this plan. He said that scientifically we should embrace everything, embrace scientifically all the institutions of Trieste, University, Sissa, and ICTP. And he used always this expression, to embrace everyone scientifically involved in the Trieste community. But I must say that that was his philosophy. But as an embracer, the official embracer was Alberto. He was the one capable to embrace everybody at Sissa, ICTP, and the Università di Trieste. I'm not thinking about pretty girls only.
No,
also. But actually, you were with Jim. You were capable to build this beautiful scientific melting pot, in which many people, as you know, have grown up scientifically. And I think on the, as you know, on the side of Italy, I should thank you for what you did there.
No, it's been for me for existing, for having been in such a beautiful country like Italy, in a place like Trieste. I thank Italy.
It was a beautiful atmosphere. Yes. Okay, I will just present the main features of this definition of regular functions over quaternions. I will illustrate the motivation to give a new definition, and some applications at the end if I have enough time. So of course on quaternions I will use the standard notation, and the idea is how to create a theory of quaternionic valued functions which is somehow play the role of the holomorphic functions in the complex case. And of course there are natural attempts very fast. If you try to define the analogues of a holomorphic function using differentiability, H differentiability, H differentiability, then what happens, you require, for example, the existence of the left limit over here, and what happens is that you only get the quaternionic affinement, so this definition is too narrow. You may try to use the H analyticity, and require that locally a function will be expandable in the generic quaternionic power series. This is a generic monomial. But if you do this, then the set is too large, because you get all the analytic maps of 4 real variables. So this extension does not make any sense. The definition that has been used together with others, but the one who has had the fortune, let's say, and has been used in many contexts, is the one due to Fueter in 1935, and is connected to the so-called Cauchy-Fueter operator, which is, as you see, is an extension of the Cauchy-Riemann operator. So the Fueter regular maps are the solution of this, the zeros of this operator. It is very well developed, many results, and also in several variables. And if you want to know the main features of this theory, there is this beautiful paper by Sudbury, which illustrates how it has been used. As for Fueter regular functions, I just very fast will say that there is a Cauchy integral formula where this differential form is over here, and this is the kernel, and the maximum modulus principle, the Liouville theorem, and the Morera theorem hold. And the Fueter regular functions can be expanded as uniform convergent series using this weird, monomials, where this is I j or k, and these are this is the real part, and these are the imaginary parts. So it's an odd expansion for irregular functions. And for example, the open mapping theorem does not hold in this theory. This is an example. This map is quite irregular, but clearly is not open because the image is at the interior. And there are other odd features of the Fueter theory. For example, the identity map is not regular, which seems very bad. And of course, the polynomials and the natural power series in polynomials are not regular as Fueter maps. And also, the zero set of Fueter regular functions can have real dimension 0, 1, or 2, and product and position of functions do not maintain Fueter regularity. So, you see, as I say, it has given many results in physics, because that operator, Cauchy-Fueter, is the Dirac operator, and there are, subtle things like the Plemelli formula, Plemelli representation formulas, and there are many applications. But nevertheless, if you want a theory in which natural polynomials and power series are included, this is not the right one. So, and there are other definitions with had less fortune. We tried to, with Daniele Struppa and other colleagues of mine, we tried to give a definition that included polynomials, natural polynomials and power series. So if S denotes the imaginary unit sphere of the space of quaternions, then you can define a regular slice regular function by means of this definition. Just what you do is the following. Definition. So you have here R, and then you have I, J, and some other place here K, and then you take the unit sphere, the imaginary sphere, which is two-dimensional, even if of course here it is one dimension. You choose I over here, and this gives you Li, which is a complex plane, and then you restrict the map to that slice, and you ask that on the restriction is holomorphic. That is a zero the Cauchy operator of that slice. Okay, it's like the Cauchy-Fueter operator resembles a Fréchet derivative, and this slice regularity is connected to the Gateau derivative in some sense. So in this, with this definition, luckily this map is regular. It is very easy to check because you just apply the Cauchy-Riemann to the restriction. You see over there, and this makes 0, and it's very easy. That's regular. Polynomials, natural polynomials are regular, and power series, natural power series are regular. Under this definition, you also can define a derivative, a slice-wise derivative. So that's the analogous to the Cauchy-Riemann derivative on a slice. This one, and is well defined only for regular functions in this sense. You can make the derivative, Coulomb derivative of power series in that natural way over there. We derive term by term to get the Coulomb derivative, and you have a nice. You see, for this definition, you have a nice power series expansion. So if B is the unit ball in H, a map from B to H is regular if and only if it has a series expansion of that form, where this one is the Coulomb derivative as 0, and this is the quaternionic variable. So this seems to be satisfactory. It includes power series and polynomial naturally. And also we have a slice-wise Cauchy representation formula. If you take in B the unit ball, if you take Q, and if IQ is the imaginary unit, Q on this slice, then you will get this slice-wise representation formula, Cauchy type representation formula, and you prove Cauchy estimates in the theorem, Morera theorem, and also the open mapping theorem holds. I'll tell you how one can prove the open mapping theorem, which is an important tool which is not available with the Fouetter theory. And I'm going now to describe as examples a few features of this class of functions, and then I'll give two applications at the end, which actually are the motivation, the real motivation to study this class of regular functions. So, zeros. Zeros of regular functions are quite interesting. This lemma states that if there exist x0 and y0 real and two imaginary units, such that for two different imaginary units the map is 0, then it is 0 on the entire sphere connected to 0 and y0. It's like if you know, for example, if you know that you have this map f as a 0 here, and then this is a two-dimensional sphere, another 0 here, this is for j, this is for I, and this is for j, this one. Then if there are two different zeros in the same sphere, then the entire sphere is made of zeros. So the zeros of this class of maps are either isolated points, real or not real, or entire two-dimensional spheres. It's like they are or empty balloons or balloons of dimension 2 in H. So it's quite nice compared with the fact that in the Fouetter case you can have dimension 0, 1, 2, or 4. Yeah, of course you don't. So this is what I just said. They are empty or balloons of dimension 2. And this, of course, this result leads to a strong identity principle. Of course, if you have a map which is 0 on a sequence which accumulates to one of those spheres, then it has to be 0 in the entire domain of definition. And while studying zeros, one encounters the necessity, it is necessary, it is important to have this regular operation of regular functions, the so-called star product. Of course, also this class is not closed for usual product. If you make pointwise product, then you don't get, given two regular maps, you make the pointwise product and the product is not regular. So you introduce this classically defined, in the case of polynomials, star product, which, the idea is you multiply two power series, just ignoring the fact that there is no commutative property. But you force, the product, the usual Cauchy product type among series. And you define also the regular reciprocal. This is the regular conjugate of power series. You just conjugate the coefficients, quaternionic coefficients, and you maintain them on the same side. And then the symmetrization of f, of the regular f, is defined as the star product between f and the regular conjugate. And then this is the regular reciprocal of a function. And this is the first idea. I mean, there are a few papers on the analogous of meromorphic maps, because this is a quotient. The only way of making a regular quotient in between the regular functions, and this first illustrates how the poles of a meromorphic map will be entire spheres or real points, isolated real points, or isolated two-dimensional spheres. And one other thing that one would like to do is to connect the definition of regularity with the possible notion of analyticity. And which kind of analyticity we can use? The so-called quaternionic analyticity. So, in the power series, you cannot, if you choose a non-real point P, quaternion P, and you want to write a power series centered at P, of course you cannot use the usual product here because it's not regular. So instead of the usual product, you use the star product between power series, and then you just make the usual infinite power series with the star product here. So you call quaternionic analytic map from omega into H if the neighborhood U of any P can be expanded in this way. Of course, the question is where does such a power series converge, which is domain convergence of such a power series. One might expect maybe that the series converge in a ball, in the usual ball with respect to the Euclidean distance, but this is not the case. In fact, if you define omega, this point V and sigma, define the distance among P and Q. The usual quaternionic distance. Sorry. Okay. So this is the usual distance, Euclidean distance, and this is something different. So this map is a distance, not topological equivalent to the Euclidean distance, and this picture illustrates how it can be computed. If P and Q are on the same slice, over there the same slice, then it's the usual Euclidean distance. Otherwise, it's like libro abierto of Alberto. Mm-hmm. And the libro abierto will appear at the end of the talk if I have time enough, because the structure connected naturally to this function is that of libro abierto. So to go from P to Q, if you want to measure the distance, you just go, you move Q, you draw the straight line, and then you just close the book again. And so the domain convergence of a series of that type, of regular power series centered at P, is a sigma ball. And the sigma ball means a ball with respect to the distance I just defined. And that's interesting because if the radius of convergence of the power series with coefficients an is smaller than the distance of P from the real axis, then it's a flat disk. It's a complex domain of convergence. It's not an open set. If the distance of P, the center from the real axis, is larger than is smaller than the radius of convergence of the power series with the coefficients an, then the domain convergence is like a flat disk and an open. It's like an open zeppelin. It's like an open zeppelin around the symmetric with respect to the real axis. Otherwise, if the center P is on the real axis, then it is usually a usual ball. And surprisingly, there are regular functions that really converge on such domain. This domain only, or this domain only, of course, the ball. And what happens is that if you have a power series, a regular functions in a ball, and then you take the point P of the ball and you make it expand in the regular power series, you can expand F in the regular power series centered at P in this way, in the usual way, and the convergence will take place in a sigma ball, one of these three possibilities, centered at P, with radius exactly the maximum possible radius, r minus norm of P, which is the distance in between P and the radius And so one can give a notion of a weakened notion of analyticity. The function is sigma analytic in the point of a domain if there is a regular power series centered at P, which converge, of course, usual stuff. So you have remember that this power series converge in general not in an open set, in one of those sigma balls. It might be also only flat disk. The regular power series P n having values of convergence R defines a sigma analytic function on a ball. And here you can expand in this sigma ball containing omega function expands like this. So it's like you substitute the idea of a ball with the idea of a sigma ball, and you get the same result as in the complex space. So it's regular. The function is regular. The quaternionic function is regular in the domain if and only if it is sigma analytic in the same domain. So this. This is one of the features. If you substitute the sigma distance with the Euclidean distance, then analyticity becomes equivalent to slice regularity. So one other feature which we like very much is the structure, the factorization of polynomials, which of course gives an idea on how one can factor out zeros from slice regular functions. So the fundamental theorem of algebra holds. We found a new proof, because this is classical. Of course, we have the regular star product between natural polynomials with coefficients on the right, because these are the only regular polynomials. You study which kind. How can you factorize polynomials? Just 3 examples. Regular polynomials of second degree. First case is the case in which the polynomial can be factorized q minus alpha star product q minus beta, which means this one. Because when you make the star product, the constant goes on the right. So if alpha and beta are not real, and if the imaginary part of alpha, the modulus of the imaginary part is not equal to the modulus of the imaginary part of beta, which means that they don't stay on the same one. They cannot stay on the same S2 sphere. So one is here and the other one is some other place. One is here and one is here. Alpha and beta. In this case, alpha is a root, the first one, but beta is not a root. Instead of beta, the root is a conjugate of beta, which stays on the same sphere as beta, and it changes according to alpha, and this is the formula. So if alpha is here, then the second root won't be beta, and beta is here, then the second root won't be beta, but will be some other point on the same sphere as 2 spheres of beta. This is called the camshaft effect on roots. This is the first case. The second case is the one in which alpha, the beta is equal to the conjugate of alpha. So if you have alpha is here, and alpha, and the other one is the conjugate of alpha on the other side, then every point of the S2 sphere is a root, so there are infinitely many roots. And the third case is the one in which is new, in some sense. It's the one in which beta is not the conjugate of alpha, but stays on the same sphere as alpha. So in this case, alpha is here, and beta is not alpha, the conjugate of alpha, but it's another point of the same S2 sphere. In this case, the only root is alpha. there isn't any other root different from alpha, and a new notion of multiplicity is given, because in this case apparently you can factor out only q minus alpha once, and beta does not contribute with a new root if we are in that situation. But nevertheless, in many situations, the multiplicity of alpha, it is clear that it has to be defined to be equals to 2. With this definition of with the definition of multiplicity connected to this example that I have been illustrating here, the degree of polynomial in the quaternionic case, of course, will coincide with the sum of the multiplicities of the roots. Otherwise, in general, with the classical definition, it's a smaller or. I mean, the degree of the sum of the multiplicity is smaller or equal than the degree of the so every polynomial can be factorized as a product of this is a spherical polynomial like q minus w star q minus w bar, the case in which alpha and alpha bar are on the same sphere, and a product of a finite number of factors of this kind and a finite number of factors of the second type, in which alpha 1 is in a certain sphere and all the others lie in the same sphere. And the product of these two kinds of factors factors out every given quaternionic polynomial. So this is the definition of multiplicity of roots that I have been describing right now. The new thing is depends on the case in which alpha and beta stay on the same sphere, but beta is not the conjugate of alpha. And otherwise is the classical definition. Okay, the open mapping theorem, I think if f is lies regular, then the modulus has a local minimum point in B, if f is defined on the sphere. Then either f is constant or f is 0 in the sphere. And then there is a geometric property which states that on a sphere, if you fix x and y, if you fix a sphere, and then you move, you fix x and y, and then you move I, you have the imaginary unit vary on the S2, then the map as a function of I is fine. This is strong geometric property, which gives us the minimum modulus principle, not the weak one, but the real one, which states what one expect. If the modulus is a local minimum P, then either P equals 0 or f is constant. And to obtain the open mapping theorem, we have to throw away the subset, subset S, which is a sphere S is said to be degenerate if f restricted to S is constant. You call the union of such spheres in which f is constant, you call them the degenerate set. And it has no interior, and if you throw this away, then you get the open mapping theorem. In fact, the open mapping theorem states the following: if f from a ball to h is non-constant and regular, and the f the degenerate set, then on the complement of the degenerate set, the map is open. This is an example of a non-open mapping because, of course, here the sphere of imaginary units is a degenerate sphere. Non-open mapping if you keep some portion of the degenerate set. I mean, this theorem cannot be improved. Also, there is a notion of axially symmetric open subset of B0R. A set is called to be axially symmetric if with every point contains the entire true sphere around the real axis. There are theorems, so if you consider these symmetric domains, what turns out is that you consider these symmetric domains and you also define the slice domains when omega intersected there is not empty, and on every slice omega intersected the slice is a connected open set in a line in this complex way. So if you combine these two notions, axially symmetric slice domains, they play the role of the domains of holomorphy for complex holomorphic maps. So you just find a substitute in this theory for the domains of holomorphy. And also there is an extension theorem which says that if you have f from omega into h, a regular map, then you can always extend in a weak way this map to the axially symmetric completion of the given domains. It's just exactly like the statement is just exactly like in the complex stage for domains of holomorphy. Okay, so the two applications I wanted just to describe, I tried to give the flavor, some results of the theory, zeros and the domain, the analogous domains of holomorphy, the notions of analyticity. But the real nice applications are that we found up to now and we were searching for. One concerns the non-commutative functional calculus. So we have power series and polynomials which are needed if you want to make a functional calculus, and we have a Cauchy formula, a slice-wise Cauchy formula, where this one is the Cauchy, it's another way of writing down the Cauchy kernel, the slice-wise Cauchy kernel, which can be written in this way. This is why you see this is the regular reciprocal of S minus Q, which can be written like this by definition, and that expands in power series in this way. If you have two-sided Banach space over H and a bounded linear operator with the usual norm, for the norm of T smaller or equal than S, over here, we can define the left S resolvent by using the Cauchy kernel series, which I illustrated just is connected to the Cauchy kernel. So for T smaller than a norm of T smaller than S, you can expand this S resolvent in this way. T is just in place of the variable, and I is the identity linear operator. So on a set in general larger than the norm of T smaller than S, the left resolvent operator can be defined directly in this way, which a priori can converge in a larger set than the one that we established at the beginning. So we can define the analogous of the S spectrum of the linear operator, the set in which this the denominator over here is not invertible, and just like in the classical Stanford case, the spectrum the S spectrum is a compact non-empty set. And so one can develop the functional calculus by setting the usual definition. And to the best of our knowledge, there isn't any other notion of a non-commutative functional calculus in the sense of Danforth-Schwarz except this.
Spectral theorem?
Spectral theorem, yes. Another application concerns, which was really quite surprising for all of us. I'll say the names at the end, but this one has been done with Simon Salomon and Caterina Stoppato, she is a student of mine, and concerns the study of four-dimensional of orthogonal complex structures in very simple set inside the quaternionic space. This is just a recall definition of orthogonal complex structures. Almost complex structures, and is the usual endomorphism of the tangent space whose square is minus the identity. It is orthogonal, of course, it preserves the metric of the Riemannian manifold, and also we want that it preserves the orientation, and it's called orthogonal complex structures if it is integer. So there is this theorem, which is quite interesting. I mean, this is, I think, is classical. I think Verjovsky has used it, but I don't know. It probably is even before the paper of Verjovsky. So if you take R4 and you just cut away one straight line or a circle, either or, and you want to, and you have an orthogonal complex structure in the complement of a straight line or of a unit circle, then if you assume that the orthogonal complex structure is not conformally equivalent to a constant one, to the constant one, then this or CS is unique up to sign. There is only one up to sign, and of course up to and the maximal and up to conformal transformations. Of course, this one will be the maximal domain definition for I. Except the case in which you cut away a straight line, either straight line or a unit circle. It was not known since the 90s what happens if you cut away, for example, just an algebraic curve of higher degree. It was not known. Surprisingly, okay, let's see. For example, in this case, it is possible to find one non-constant orthogonal complex structure using the Alberto libro abierto structures, which I like very much as an expression. I mean, so you multiply, you take V, which is a quaternion connected to the imaginary unit IQ. I mean, sorry, EQ. Yes, EQ. You take the imaginary unit connected to Q, and on that tangent space, the orthogonal complex structure will be take V and multiply V on the left by the imaginary unit of Q. And this is exactly the one which preserves the slices, the page of the libro abierto. And this is the unique. This is unique. This is the only. This is the only orthogonal complex structure on H minus the straight line. It seems a very. I mean, it's a very simple problem, but the solution it took a while. And then, except the case of the circle and the straight line, nothing was known. So, what happens if you cut away some other piece from H, different from a straight line or a circle? Okay, of course you use the fact that the real differential f star of an injected regular function, sliced regular functions, is invertible at all points, and one can push forward the complex structure J defined on H minus A, on the libro abierto. So we have the natural complex structure which I just described here, this one. And you push forward using the differential of an injective regular function, which is always invertible. That's the natural way of making the push forward. And we were able, using the knowledge of the roots of the quaternionic polynomials, how they behave in H when you move the image of the polynomial, we could, we took H and then we chose a parabola. So this is f from H minus the real line to H minus the parabola, of course this one. And we push forward and f is injected when restricted either to the open right half space of real part greater than 0 or to the open left half space h minus 0. And what happens is the boundary of h plus and h minus, which is the imaginary tree space, maps onto the three-dimensional paraboloid, onto a paraboloid which is three-dimensional. Of course, the interior is an empty interior, and so an f of h plus is h minus the paraboloid, and f of h minus is again h minus the paraboloid. And this allowed to define a single value of the complex structure on a dense open subset of h minus the parabola. And the theorem is as follows. So you have two complex structures, one induced by the restriction of f to h plus, and this is defined on h minus the parabola minus the paraboloid. And j minus is induced by f from h minus to h, again on h minus the parabola minus the paraboloid. And this is the maximal open domain definition for the two complex structures, and they can be extended continuously to boundary gamma of the paraboloid in the tree space, but neither of them extends continuously to any point of the paraboloid minus the parabola. So it's difficult to make a picture for dimensions, of course, but this is the parabola, and this is the paraboloid in the tree space. They do not actually intersect, and what happens is you have two different complex structures, exactly two, and that's the all possibilities, defined on h minus the parabola and minus this paraboloid, entire paraboloid, which remember is empty interior in R4. And it turns out that it's impossible to define an orthogonal complex structure on the complement of h minus the parabola. And the fact that it's not possible to do that is a result of a theorem of Verjovsky. So we prove that if you take out a parabola, then you have exactly two, except the constant one, you have exactly two orthogonal complex structures, not equivalent, and of course minus 10, and that's all, up to conformal transformations. Other examples of topics under investigation are the Laurent series and the residue theory, and then point-rate type geometry in unit ball of H, Schwarz type and boundary rigidity that I think Fabio Blacci will illustrate in his talk. And then we found the analogous of Ehrenpreis Lagrange lemma for polynomials with quaternionic coefficients. You know, there are many directions, and this class of functions is quite surprising properties. And actually, the thing which I would like to push forward now is this subject together with Simon Salomon concerning orthogonal complex structures, because the idea is that this libero abierto structure and the slice regular function seems to fit exactly well together to produce examples of this kind of orthogonal structures in subsets of H. Of course, there are extensions to Cayley numbers, and somebody is taking care of the general Clifford algebras and several variables. There are many directions. This is the first the paper in which we defined the two papers in which we gave the definition in 2006-2007 with Daniel Struppa, and then the fundamental theorem, zeros, extension results to be analogous to the domains of holomorphy kernels, and then the non-commutative functional calculus. And the compendium of this theory will appear soon, this January or February, in this monograph of the spring paper. Okay, thank you very much.
Well, thank you very much. Are there any questions?
Yeah, have you investigated as to which contact four manifolds might emit applices which have of regular functions?
Yeah, that's difficult because you know the problem of the composition of regular, even for slice regular functions, the composition is in general is not regular.
Right.
So that's the problem. But you're right. What we are doing, the nice manifolds, quaternionic manifolds, except the quaternionic projective space, the Simon Salomon knows very well. We are producing the moduli spaces of quaternionic tori. For the tori, of course, this is perfect because we are capable to characterize the group of regular automorphisms of H, which are still affine. Okay. And so we can find, we can study the quaternionic tori, and this is very nice. You have this, of course, this reticuli, lattices, and you classify the lattices like you do in the complex case, but of course it's much more complicated because it involves all definite subgroups of the S3 spheres of quaternions. But we are producing the moduli spaces for quaternionic tori, which are a class of manifold, quaternionic manifolds that can be defined as you suggest. In general, it's not possible because unfortunately the composition is not in general regular. There are special cases, and one is this one.
Is there any hope of proving something like the version of the Riemann mapping theorem? So let's be more precise. Suppose you have two open regions bounded by smooth spheres. Do you know if there exists a regular map from one to the other?
The problem that is not you know, the proof that we usually do in the complex case involves the logarithm, and the quaternionic logarithm has many problems. So the proof cannot be replicated. Of course, a subclass of domains, those which are symmetric,
or complex boundary, for instance.
Yeah, I mean the case of symmetric slice domains. If both domains are slice symmetric, then they are biolomorphic. But then you use the slice-wise, you use the Riemann mapping theorem slice-wise. Exactly. But in general, it's not. In general, I don't know. Really, I don't know.
I was trying to prove the differential with Poincaré conjecture, but.
A similar question being, if you have a diffeomorphism of S3, which of those extend to regular quaternionic functions on the unit quaternion ball?
Regular functions, in general, you mean like the Cauchy-Riemann CR structures?
No, like the extension of conformal mappings of the circle to the unit disk.
No, here we have that.
No, you have that. You have that because if you have one of those slice domains, then you can extend a map given on the unit circle. You extend it inside, and then with the extension theorem, you extend to the symmetric completion of the domain. So you have that. Understand your question? Yeah, that's possible. Of course, on this class of special domains.
But another question, last question. I mean, it's tempting to do dynamical systems of the quaternion, like rational functions, but I don't think it's possible, no, except for.
You know, the problem is the composition. Composition is the problem. Still, again, you want to compose to make a dynamical system, and this, I mean, there are sub cases in which it can be done, but in general, it's not easy. If Fabio will. I don't know if he'll say something in the next talk, but he's studying when one can obtain regular compositions of regular maps, which is not easy. Some other approach, I mean, one thing that can be defined is the composition operator. If you can define the analogous of HP spaces, RD spaces, of regular functions on the ball of H, and then you have a regular notion of regular Möbius transformation, and then you can use that to make the usual composition operator.
Ah, okay.
And there is an attempt to make dynamical systems in that sense.
Composing with those.
Exactly.
Like a star composition.
Exactly.
Okay.
Exactly.
Any other questions? So we can speak early.